Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the fourth video of week 10. Here we come to chapter 6 on cooperative games. In the chapters 1, 2, 3 and 5 we have treated non-cooperative games, so games where people have strategies. Now we come to cooperative games. The basic definition is simpler and quite different, but we will see that they are surprisingly useful and the theory is surprisingly rich. So now I start first with the basic definition and then I make a lot of informal remarks before I start to develop the theory. Definition 6.1. A cooperative games is a pair A-V where A is again a set of players, set players 1 to M as usual, and this V is a map from the power set of A, so the set of all subsets of A, to the real numbers, such that especially the value of the empty set is 0. So this V is called coalition valuation or characteristic function. So V for valuation. So V associates to any subset of A real number. So the subsets then will be called coalitions and these real numbers will be the coalition values. Yeah, this is new, this concept. In all the preceding chapters we have considered non-cooperative games. All the players were fully rational and were interested only in their own utility. The other player's utility was relevant only because the other player's utility guide their decisions and their decisions have implications on their own utility. So in the cooperative game now it's different. There people can form a coalition and then they get a joint utility, namely the coalition value. And the distribution of that utility within the coalition is not central. That depends on further assumptions and it's not part of the theory which I develop in this course. So, but there are some technical terms about this. This is called transferable utility or non-transferable utility. So in the simpler cases, one assumes transferable utility. That means that the utilities, this joint coalition value can be distributed freely within the players in one coalition. And they can compare the single utility. So this number has the same meaning for all of them. There's also a more exotic case of non-transferable utility, where the utilities of the different players might not be comparable, might not be shiftable. So, but we will not treat this case at all. But there exists this technical term. So it's not part of the theory which I develop here, how the coalition value is distributed within one coalition. So the notion of cooperative games, which I just proposed, is rather elementary. It's in some sense very poor. Many features of games which we have seen before are not present here. We don't have strategies, we don't have periods, we have almost nothing. We just have players and for any coalition we have a real number. But we will see that this notion is still very relevant and useful and the theory around it, which I will develop, is quite rich. So there are two solutions concepts for cooperative games. One is the proposal of a single vector of real numbers, of m real numbers, which should give each player his part of the whole utility, which can be distributed. So the coalition valuation function tells us somehow how powerful one person, one player is. And one can then try to extract from that information how much of the utility which can be distributed he deserves. So in the single vector is in the proposal of such a fair or reasonable or proper or just distribution. So the other solution concept is the proposal of not a single vector but of a whole set of such vectors. So it makes sense not to consider always a single solution vector, but a whole set of sufficiently good solution vectors. So this we will do next. In this section we will consider two solution sets. First the set of imputations and then a bit later the so-called core of a cooperative game. Later in section 6.4 we will consider also a single solution vector, namely the so-called Shapley value, or also called Shapley-Shubik index. So there is some theory behind it. It's non-trivial, but it is quite useful if one tries to measure, for example, the voting power of members of some parliament, or of members of some committees where coalitions can be formed and where people can have a vote. So there are many more indices which can be found in the book of Holle and Illing from 2009, but the Shapley value is the single most important one. And we will treat that in the final section 6.4. So now a basic technical remark. If you have a fixed set A of players 1 to m, then the set of all cooperative games is isomorphic to R up to 2 up to m minus 1. And this is of course a vector space, R vector space of dimension 2 up to m minus 1, but the vector space structure is not really important. So and the association of such a vector to any cooperative games is very elementary. We just take the tuple of the collision values in a suitable order. So the collision value of the empty set is taken out because it's 0 anyway, but the other values, they are 2 up to m minus 1, they are just listed, and this gives them this vector of real numbers. So yeah, the old book of von Neumann and Morgenstern from 1944, which was somehow the birthplace of game theory, had quite a part about cooperative games. And especially they had something which now looking back is not so important anymore. They had several recipes how to go from a finite game in normal form to a cooperative game. And two such recipes will now be exemplified in one example, which I took from a lecture notes from Jäger from course on, I think, on game theory in 2007-2008 in Regensburg. So the examples are from Jäger, but the concepts are from von Neumann Morgenstern. But let me stress again, this is somehow not so important. I give this example because this was somehow historically important and it gives a connection between strategic games and cooperative games, but this connection is not really so important. We will not come back to these examples later. So, but we start with an interesting game in normal form. Here you see a finite 3-person game in normal form where each player has 2 strategies, small a and small b. And you see the values here in the table. It has some similarity to the prisoner's dilemma. So for each player, the strategy B is dominant, but if all choose B, they are all quite poor. If all would chase A, they would all be much better off. So you see, let's look just at the values for a moment. If all 3 have chosen A and then one thinks whether to turn to B, then his utility will increase from 4 to 5, but the other 2 players' utilities will decrease from 4 to 2. Then if a second player also has to think between whether he chooses A or B, if we start with AAB and now player 2 has to think, then suppose we are here, and then now player 2 thinks, and he goes to this situation, then if he changes from A to B, his utility increases from 2 to 3, but the of player 1 decreases from 2 to 0, and of player B 3 decreases from 5 to 3. So now finally, if we are here now in player A, that player 1 has to choose between A and B, then he has to choose between 0 or 1, and if he chooses B, he gets 1, but the other 2 players' utility decreases to 1. So this shows that for all the 3 players, the strategy B is dominant. But if they could cooperate and would all choose A, they would get, of course, together much more. So it is quite close to the prisoner's dilemma. So now the following 2 recipes had been considered by von Neumann Morgenstern and by Jäger how to get a cooperative game out of this situation. So, and I call the two corresponding cooperative games A V1 and A V2. And I will use some notion which generally is a known notion. So this S upper B for B a coalition means a partial strategy combination, partial namely the strategies for the players in the set B. So a whole strategy combination then splits into SB and S minus B, the part for the players in the subset B and the part for the players outside the subset B. So in the first recipe, the idea is that we have a fixed coalition B, and the utility will be the sum of their utilities of a strategy combination. So the coalition value here will be a sum of utilities of the players in the subset B. And now it arises as follows. One assumes that the players in the subset B have to choose first, and the other players choose second, and the other players are as mean as possible. So they want the worst for the players in the coalition B. So whatever strategy, partial strategy combination SB the players in the subset B have chosen, the other players will choose their part as A minus B in order to get the infimum over all possibilities. That's here. And afterwards, so because the players in the subset coalition B know this, then a priori they have to try to get the supremum out of all these possible values. So they take the supremum over the infimum over these sums. So that's how this first recipe arises. The coalition value is in this value, and because everything is finite here, this is well defined. So here the other players are as mean as possible, and they don't care about their own utilities. They care only about the sum of the utilities for the players in the coalition B, and they choose second. The players in the coalition B choose first. So in this way we get for each coalition a coalition value, and this gives us a cooperative game. So the second recipe is here. Again, the players in the coalition B have to choose first. So again, the coalition value is a sum of utilities of the players B for some strategy combination. And again, of course, the players in the subset B have to choose first, and the players in the complementary coalition A minus B choose second. But now the other players don't care about the utilities of the players in the subset B. They care about their own utilities. More precisely, they care about the sum of their own utilities. So whatever partial strategy combination the players in the subset B have chosen, the others will choose their partial strategy combination, which is here, in order to maximize the sum of their utilities. So, and again, the players in the coalition B know that. So a priori, they have to find the best partial strategy combination in order to maximize the sum of their utility values. So this is how this coalition value V2 of B arises for any coalition B. So now I will present a table where you can see which strategy combinations the players in the subset B have chosen and which value then they can get from this strategy combination. So in the first line shows the possible 7 non-empty coalitions. Then the second and third line show the values for the first cooperative game, and the lines 4 and 5 show the data for the second cooperative game. So let's start with the first cooperative game, or maybe we could look at both of them simultaneously. So if B is the full coalition, there is no complementary coalition, and it's easy. They just want to maximize the sum of their utilities, and if they all have chosen AAA, they get 4 plus 4 plus 4, 12, which is better than any other value. So the others are 2 to 5, which is 9, or 0, 3, 3, which is 6, or 1, 1, 1, which is 3. So 12 is the best. So that is easy for both games. In both games they will choose AAA, in both games they will get the value 12. So if now B is the collision of the players 1 and 2, then the player, and if they choose, for example, AA, then player 3 has to think whether to choose also A or whether to choose B. B is dominant, so for him B is better, and also for the players A and 2, B is worse, because if he chooses A, then we have AAA, and the first two players get 4 plus 4, which is 8. If he chooses B, the first two players get 2, 2, which together is 4. So strategy B is dominant for this third player. So in the second game he will choose B because it's better for him. In the first game he will choose B because it's worse for the other two. So in any way he will choose B, and therefore for AAB the first two players get 2 plus 2, which is 4. So now this explains already these first two columns here. This explains already these columns here. We have seen this situation already. Now this story is more difficult for the rest. Now B consists of a collision of one single player, maybe player 1. So he has to choose between A and B. If he chooses A, then the complementary coalition, the players 2 and 3, have to decide what they choose. So they have the choice between AA, AB, BA, and BB. And if player 1 has chosen A, and they also choose AA, then he gets 4 and they get 8. If they choose AB or BA, player 1 gets 2 and they get 7. If they choose BB, player 1 gets 1 and they get 2. So in the first game, they would give him 1. No, if he chooses A and they have both chosen B, then he would get 0 and they would get 6. So if they both choose B, then in the first, if he chooses A in the first game, they would choose B, then player 1 would get 0. And in the second game, they would choose AA, because then they would get 8, which is maximum for them. So if player 1 here chooses A, then in the first game he gets, in the first game they choose BB, and then he gets 0. In the second game they choose AA, and then they get 8. Now if player 1 chooses B, then they again have the choice between AA, AB, BA, and BB. If they choose AA, he gets 5 and they get 4. If they choose AB or BA, he gets 3 and they get 3. And if they choose BB, he gets 1 and they get 2. So if they choose BB, then he gets 1. Player 1 gets 1. So, and if they choose AA, they get 4 and he gets 5. So in the second game, they will choose AA, because then they get 2 plus 2, which is 4, compared to 0 plus 3 or 1 plus 1, which is 3 or 2 less. So you see here, if the first player chooses B in the first game, the others will reply with BB and he will get 1. If he chooses A, the others will reply with BB and he gets 0. So he should choose 1 here. He should choose B here. Then his value will be 1 in the first game. If in the second game he chooses B, the others will reply with AA, because then they get 4. But then he will get 5. And yeah, and if he chooses A and the others will reply with also with AA, then he will get 8. But he will get only 4. So here they get 4 and he gets 5. And they get here 8 and he gets 4. So also in the second game, it's better for him to choose B, because then he will get 5 if the others choose AA, because if he chooses A, he will get only 4 if the others choose AA. So also in the second game, the choice B is better, but now his utility or his collision value is bigger one, it's 5, because the others react then with AA, not with BB. So a good part of these games are the same, but you see in the collisions with only one player, the situation is quite different. And you see from my long talking that it's not easy to analyze a situation. The basic definitions were easy. The game was not complicated, but still it is a lot of cases which one has to follow. So that is typical for these cooperative games. In order to analyze a given game in detail, it's usually quite some work. One has to discuss several cases. So, but as I said before, these two recipes from games in normal form to cooperative games are not so important now looking back, so we will not take them up later again. From now on, the focus will be on the cooperative games themselves, their properties and their solution concepts. So in the next video, I will start to develop the theory of the cooperative games themselves. Thank you very much.